Yeah, so let's take a look at a couple of problems from chapter 10. So these two problems I picked because they're essentially the two basic types of problems that I'd expect you to be able to solve as you get through chapter 10. So first one is going to be finding the moment of inertia for the shaded area around the x-axis. So we've got be careful, it's not actually a quarter circle. If you make the mistake to think it's a quarter circle and you go to the back of your book, you're going to be incorrect. So in this case, we're going to have to use integration. So we need to pick either a horizontal, a vertical strip, run it from one end to the other, and apply the formulas to get the moment of inertia around the x-axis. So here we are, all one sheet. So I decided to use a horizontal piece, right? So we need to know what the area is for that horizontal piece, as I've done here, right? So it's x long dy wide, so x times dy. And of course, you know you can't integrate x's and y's, right? So what we need to do is we need to be able to express x in y's, right? So nicely enough, right, that line on the outside, that curve was given to us as y equals 1/8 x cubed. So we can solve that for x, which I've done there, right? Then I can substitute that in for x, and lo and behold, my dA is going to become 2y to a third dy. Right, so how do I find my moment of inertia around the x-axis? Y squared times dA, integrate that over the limits. So that slice, right, is going to start at 0 and it's going to go up to 8. So you see my limits are 0 and 8, right? The y squared and the dy that I put in there to begin with. You can see there, I did the math as we went through, combining the y's together in the first line underneath there, and did my integration, right, applied my limits, and got an answer of 614.4 meters to the fourth for that problem. So you go. There is an example from the first part of chapter 10, one simple one I'd expect you to be able to do, of picking a strip, using integration to find the moment of inertia around an axis. So the second one I'd expect you to be able to do is the composite areas. So in this particular case, this problem is actually kind of a nasty problem for a reason I'll mention to you in a second, right? A I-beam, the location of the centroid is dead in the center. This is not an I-beam, it's a T-beam. So there's more area on the top than there is on the bottom. So the centroid isn't in the center anymore. So what they want you to do is find the moment of inertia around the centroid. But they don't tell you what the centroid is, and it's not an I-beam, so it's not directly in the middle. So this problem essentially has two steps. Step number one, find the centroid. Step number two, jump to the back of your book and find your IX values based upon setting X where the centroid is. If that makes any sense. Hopefully it will. We can see the problem. So two shapes, right? We got two rectangles. One's horizontal, one's vertical. That was my book falling on the floor. And you'll see they're actually the same size. They're both 150 millimeters by 20 millimeters. Bases and heights are different, which for the centroid doesn't make any difference. But when we get to finding the moment of inertia, right, we're going to find that the moment of inertia for the x-axis is 112 base times height cubed, and the bases and heights flip-flop, which obviously makes a differential based upon which one you cube. So anyways, right, so we're finding our centroid. So remember how we do that is we get our areas, right? They're both going to be 150 times 20. It's going to be square millimeters, right? We got to find where the centroid is, right? That y distance for each one of those. Again, they're both rectangles, so they're going to be in the middle, right? Then we multiply y times a, we take the sums, and we can find y, and we come out to 52.5 millimeters. Now that is the distance from the top down to the centroid axis. So now we're going to use that information to find our moment of inertia. And again, we're using a table. So for each of these, we need to know the area. Right? Areas are the same as they were before. Now we need to know the distance from the centroidal axis to the centroids of each of the elements. So you see the way this is labeled, that x dash slash, yeah, I guess it's slash. That x that's the x-axis that we're going off of, right? C1 and C2 are the centroids for those two pieces. We need to use the parallel access theorem here, so we need to know what those distances are. Turns out they're both 42.5 millimeters, right? One's up 42.5, the other's down 42.5 millimeters. The IX piece, the next column over, is the one that I just already mentioned to you, right? Right from the back of your textbook, if you find a rectangular area, you'll see that IX equals 1/12 base times height cubed. You need to make sure that you have the bases and the height cubes separate, right? They flip-flop, right? So for the one on top, right, you got 150 for the base and you've got 20 for the height, right? For the one on the bottom, you got 150 for the height and you got 20 for the base. So you can see those numbers are plugged in. We've got the area times that dy squared, and we have the last column is those IX values calculated out. So we do all that and we find our IX value and it's given to us there. So the second part of this problem asks us to find the moment of inertia through the y-axis. So again, if you look at your textbook, you'll see that Iy is 1/12 height times the base cubed. Pretty convenient. So in this particular case, right, the axis, both your centroids are going to sit on the axis, right? That y-bar axis bisects both of them. So all we need to do is find it for each piece and add it together, just what they've done there. So you can see the math for that one. They've done that, and there you go. So those are the two types of problems that I expect that you'll be able to do from Chapter 10. Integration and building your table and doing it composite bodies, known bodies.